inside the machine. So, in this chapters, we will discuss how the lower level terms of CPU. So, we're gonna look more on the hardware side rather than on the software. So, to do that, we need to start with basic computing concepts. Modern computers come in all shapes and sizes, but as diverse as computers are in their outward forms and in the uses to which they're put, they're all amazingly similar in basic function. At the heart of modern computer is the microprocessor, also commonly called the central processing unit, a tiny square silver of silicon that's etched with a microscopic network of gates and channels through which electricity flows. This network of gates, transistors, and channels, wires or lines is very small version of the kind of circuitry that we've all seen when cracking open a television remote or an audio or an old radio. So despite different in sizes such as TVs that could be as big as a car, any computer uh, provides this basic function, and we will gonna discuss that. That function is usually started with this representation instruction data, and you have a result. So the calculation model of computing. For the purpose of our initial discussion, we can generalize by saying that the code stream consists of different types of arithmetic operations, and the data stream consists of the data on which those operations operate. So this we can start with saying that this instruction is that arithmetic operations, since we've all been accustomed with math, and the data stream consists of the data on which those operations operate. The result stream is made up of the result of these operations. Figure 1.1, a simple representation of a general purpose computer. To illustrate this point, imagine that one of those little black boxes in the code string of figure 1.1 is an additional operator, a plus sign, and the two of the white data boxes contain two integers to be added together, as shown in figure 1.2. So here's another representation of that. So the additional operator, a plus sign, and the two of the white data boxes contain two integers to be added together. So for the data are the white boxes consisting of 2 and 3 to be added. So the arithmetic is those little block boxes, this addition, and these are the result. Thus the two input streams, the code stream and the data stream, represent sequence of key presses, arithmetic operator keys, and number keys, while the output stream represent the resulting sequence of numbers displayed by the calculator screen. Now let's move to the file clerk model of computing. What's more accurate model of computing, though that's not as accurate as the computing today. That's useful as a starting point. So here we're gonna relax it more and more, just like we did with the operating system. The file clerk model of computing. The calculator model of computing, while useful in many respects, isn't the only or even the best way to think about what computers do. As an alternative, consider the following definition of a computer. A computer is a device that shuffles numbers around from place to place, reading, writing, erasing, and rewriting different numbers in different locations according to a set of inputs, a fixed set of rules for processing those inputs, and the prior history of all the inputs that the computer has seen since it was last reset. until a predefined set of criteria are met that cause the computer to halt. So we might after Richard. So let's discuss this first. Later we will input some real world data here in this definition. So a computer is a device that shuffles numbers from place to place, reading, writing, erasing, and rewriting different numbers in different location according to a set of input. A fixed set of rules for processing those inputs, because usually you need to uh, align with the programming language, and the prior history of all inputs that the computer has since it was last reset. So it has the record of the prior inputs, which made the computer now different, which we're gonna discuss later, until a predefined set of criteria are met that causes the computer to halt. We might, after Richard Feynman, call this idea of a computer as a reader, writer, and the modifier of numbers, the file clerk model of computing, as opposed to the aforementioned calculator model. In the file clerk model, the computer accesses a large, theoretically infinite store of sequentially arranged number for the purpose of altering that store to achieve a desired result. So Richard Feynman proposed an idea of a computer as a reader, writer, and modifier of numbers, the file clerk model of computing, as opposed to the aforementioned calculator. In the file clerk model, the computer accesses a large, theoretically infinite store of sequentially arranged numbers for the purpose of altering that store to achieve a desired result. So we have to alter that or modify that store to with a fixed process to achieve a certain result. Once this desired result is achieved, the computer halts or stops, so that now the modified store of numbers can be read and interpreted by humans. In a nutshell, a computer device is a device. Computer is a device that reads, modifies, and writes sequences of numbers. These three functions, read, modify, and write, are the three most fundamental functions that a computer performs, and all of the machine's components are designed to aid in carrying them out. So these three functions, read, modify, and write, are the three most fundamental functions that a computer performs. So we're gonna see these as true in each level of computing. In fact, this is actually how we discuss the thesis to make it simpler for professors, because it's true in all level of computing. So let's input this to the description we defined earlier. A computer is a device that shuffles numbers around from place to place, reading, writing, erasing, and rewriting different numbers in different locations according to a set of inputs. Read, a fixed set of rules for processing those inputs. Modify, and the prior history of all the inputs that the computer has since it was last reset. Right, until a predefined set of criteria are met that cause the computer to halt. The stored program computer. All computer consists of at least three fundamental types of instructions needed to carry out the read, modify, write sequence. So for us to be able to mimic that operation, it started from these three fundamental types of structures. First, storage. To say that a computer reads and writes numbers implies that there's at least one number holding structure that it reads from and writes to. All computers have a place to put numbers, a storage area that can be read from and written to. Arithmetic logic unit, ALU. Similarly, to say that a computer modifies numbers implies that computer contains a device for performing operations on numbers. Similarly, to say that a computer modifies numbers implies that the computers contains a device for performing operations on numbers. So there must be a device that perform the calculation, such as the calculator, right? Like the calculator. This device is the ALU, and it's the part of the computer that performs arithmetic operations, addition, subtraction, and so on numbers from the storage area. First, the numbers are read from storage into the ALU's data input port. Once inside the ALU, they're modified by means of an arithmetic calculation, and they're written back to storage via the ALU's output port. So first, you need to read that from storage. You need to have some storage somewhere, and then put that into the input port of this calculator. Once inside the ALU, they're modified by means of an arithmetic calculation, and they're written back to storage via the ALU's output port. Note that ALUs are normally understood as having code input port. Uh, Along with their data input port and results output port. They do, of course, have command input lines that let the computer specify which operations the ALU is to carry out on the data arriving at its data input port. So they have the command, just like the command we have in input-output device. So while the depiction of a code input port on the ALU in figure 1.1 is unique, it's not misleading. So it doesn't actually have this code input and data, but for the starting point, just like with operating system, as we relax this, it's actually useful as a starting point. So another component is bus. In order to move numbers between the ALU and storage, some means of transmitting numbers is required. Thus, the ALU reads from and writes to the data storage area by means of the data bus, which is a network of transmission lines for shuttling numbers around inside the computer. So to move that, we haven't discussed the process. So there must be some physical way for us to move the data from storage to ALU. Some means of transmitting numbers is required because that's the basic or the initial action or command that our ALU can be configured to do. Thus, the ALU reads from and writes to the data storage area by means of the data bus. So the way to communicate that is by means of a data bus, kind of like how OS communicate with I/O. It needs to put the data first, and then the execute the command, and then send the status. So the way to send the status, you must have some bus in some way. So we also discussed that in the I/O chapter, in which the nearest bus or the GPU and the lower or the slower bus are farther away. And we also discussed there the DMA devices that special device that allows to make the copy fast in the OS. Instructions travel into the ALU via the instruction bus. but won't cover how instructions arrive at the ALU until chapter 2. So an instruction actually traveled to this ALU via a specialized instruction bus. So that's for instruction. For now, the data bus is the only bus that concerns us. So there's actually two different buses for instruction and data, kind of like the different bus or the different way we connect to command and data with I/O devices. But for now, let's simplify it. So the code stream in figure 1.1 flows into the ALU in the form of a sequence of arithmetic instructions: add, subtract, multiply, and so on. So for now, let's just do the basic operations. Later we will add some memory operations as well. The operands for these instructions make up the data stream, or the command for these instructions make up the data stream. This flows over the data bus from the storage area into the ALU. As the ALU carries out operations on the incoming operands, the result stream flows out of the ALU and back into the storage area via the data bus. So these are more relaxed view of how it actually works. So the code stream flows from this separate code storage, then goes to the ALU, flows into in the form of a sequence of arithmetic instructions. The operands for this instruction make up the data stream. So the operands, or the plus, negative, multiplication and division, are made of the data stream, which is this. This flows over the data bus from the storage area into the ALU. As the ALU carries out operations on the incoming operands, the result stream flow out of the ALU and back into the storage area via data bus. So it flows out here. So simple. So just like before. So this process continues until the code stream stops coming into the ALU. So here, as you can see, the result comes out on the data bus rather than the instruction bus. Figure 1.3 expands on figure 1.1 and shows the storage area. So we just expand this. The data enters the ALU from a special storage area, but where does the code stream come from? One might imagine that it comes from keypad of some person standing at the computer and entering a sequence of instructions, each of which is then transmitted to the code input port of the ALU. Or perhaps that the code stream is a pre-recorded list of instructions that is fed into the ALU. Or perhaps that the code stream is a pre-recorded list of instructions that is fed into the ALU by the programmer, one instruction at a time, by some manual or automated mechanism. Figure 1.3 depicts the code stream as pre-recorded list of instruction that is stored in a special storage area, just like the data stream. As a pre-recorded list of instruction that is stored in a special storage area, just like data stream. And modern computers do store the code stream in just such a manner. So the instruction and the data are separate. The code is in a separate special storage area, just like the data stream that contains the operands. And modern computers do store the code stream in just such manner. Note, more advanced readers might notice that figure 1.3 and figure 1.4 later, I've separated the code and data in main memory after the manner of a Harvard architecture level 1 cache. In reality, blocks of code and data are mixed together in main memory. So just like the heap we discussed and the stock and the code in the operating system. But for now, I've chosen to illustrate them as logically separated. The modern computer's ability to store and reuse pre-recorded sequences of command makes it fundamentally different from the simple calculating machines that preceded it. Prior to the invention of the first stored program computer, all computing devices from the abacus to the earliest electronic computing machines had to be manipulated by an operator or group of operators who manually entered a particular sequence of commands each time they wanted to make a particular calculation. So this sets it apart from other calculator or calculating device in which it is more precisely called stored program because it remembers the previous input and the previous calculation that do not require human uh, entering a sequence of commands, therefore reducing cognitive load or more especially for repetitive tasks. So refining the file clerk model. In this example, the code stream consists of a single instruction, an add which tells the ALU to add two numbers together. The add instruction travels from code storage to the ALU. For now, let's not concern ourselves with how the instruction gets from code storage to the ALU. First, obtain the two numbers to be added, the input operands from the data storage. So you need to obtain the two numbers to be added from the input operands. So for now, let's not concern ourselves with how instruction gets from code storage to the ALU. First, obtain the two numbers to be added, the input operands from data storage. Second, add the numbers. Third, place the result back into the data storage. So we kind of did that earlier. So the preceding example probably sounds simple, but it conveys the basic manner in which all computers operate. Computers are fed a sequence of instructions one by one, and in order to execute them, the computer must first obtain the necessary data. So it's kind of like the I/O device where you need the data first before you can execute the command. So here you obtain the two numbers to be added, the input operands from the data storage. Then perform the calculation specified by the instruction. So the calculation are specified by instruction and it is stored from different or special storage. And finally, write the result into a place where the end user can find it. Those three steps are carried out billions of times per second on a modern CPU. Again and again and again. It's only because the computer executes these steps so rapidly that it's able to present the illusion that something much more conceptually complex is going on. To return to our file clerk analogy, a computer is like a file clerk who sits at his desk all day waiting for messages from his boss. Eventually, the boss sends him a message telling him to perform a calculation on a pair of numbers. The message tells him which calculation to perform and where in his personal filing cabinet the necessary numbers are located. So imagine a clerk inside in a filing cabinet. That filing cabinet is the data where the clerk will perform its calculation. So the clerk first retrieves the numbers from his filing cabinet, then performs the calculation, and finally places the result back into the filing cabinet. It's a boring, mindless, repetitive task that's repeated endlessly, day in and day out, which is precisely why we have invented a machine that can do it efficiently and not complain. The register file, since numbers must first be fetched from storage before they can be added. We want our data storage space to be as fast as possible so that operation can be carried out quickly. Since the ALU is the part of the processor that does the actual addition, we'd like to place the data storage as close as possible to the ALU so it can read the operands almost instantaneously. So because we need the data first from the data storage for us to execute or modify this input and provide an output, that storage need to be as close as possible. So that leads to the design of this CPU. However, practical considerations such as CPU's limited surface area constrain the size of storage area that we can stick next to the ALU. This means that in real life, most computers have a relatively small number of very fast data storage location attached to the ALU. These storage locations are called registers, and the first x86 computers only had 8 of them to work with. These registers, which are arrayed in a storage structure called a register file, store only a subset. These registers, which are arrayed in a storage structure called a register file, store only a subset of the data that the code stream needs. And we'll talk about where the rest of the data lives shortly. So it's actually an array of a register called register file, and it only store only a subset of data from the code stream, such as from instructions and data input. Building on our previous three-step description, what goes on when a computer's ALU is commanded to add two numbers, we can modify it as follows. To execute an add instruction, the ALU must perform these steps. Obtain two numbers to be added, the input operands from two source registers, so since we have this array of register near the ALU, we need to obtain it from that two registers, from that two, and then the ALU will now add the number, then place the result back into the destination register. It's still near the ALU before it can transfer it to back to the storage for user interpretation, or for user screen. Usually for Pixel, it could be listening to music, or it can be watching a movie. Any thing that provided by internet is basically works this way. You get the input from the register, perform a calculation, put that into the destination register, get it back to the storage for show to the user. So for a concrete example, let's look at addition on a simple calculator with only 4 registers named A, B, C, and D. Suppose each of these registers contains a number. For a concrete example, let's look at addition on a simple computer with only 4 register named A, B, C, and D. Suppose each of these registers contain a number, and we want to add the contents of 2 registers together and override the contents of a third register with the resulting sum as in the following operations. So here we have code. These are our code instruction. Add a plus b and then override the c. Another thing, like we discussed in the operating systems video, most of this data do not actually equate or is not actually deleting data. They're just overwriting it. So the previous data are just being overridden and they're not actually deleted. So here it means add the contents of register A and B and place the result in C, overwriting what was there. Upon receiving an instructions commanding it to perform this addition operation, the ALU in our simple computer would carry out the following three familiar steps. Read the contents of register A and B, to add the contents of A and B, write the result to register C. Right? Note, you should recognize these three steps as a more specific form of the read, modify, write sequences from earlier, where the generic modify step is replaced with an addition operation. So the modify, you can think of that as replaced with an addition operation. It's still the read, modify, write sequence. So these three step sequence is quite simple, but it's at the very core of how a microprocessor really works. In fact, if you glance ahead to Chapter 10's discussion of the Power PC's 970's pipeline, you'll see that it actually has separate stages for each of these three operations. Stage 12 is the register read step. Step 13 is the actual execute step, or the modify, and stage 14 is the write back step. Don't worry if you don't know what a pipeline is, because that's a topic for chapter 3. Basically, the pipeline kind of like the instructions, a set of instructions being done to process those data. Of course, there is other like commands to get into that till stage 12, and then to 14, and from 14 to latter. But yeah, that's the basic. So the 970's ALU reads two operands from the register file, adds them together. So again, the 970's ALU reads two operands from the register file. So the register file, source register file, adds them together and writes the sum back to the register or destination register file. If we were to stop our discussion right there, you'd already understand the three core stages of the 970's main integer pipeline. All other stages are either just preparation to get to this point, or their cleanup work after it. So it's all other preparation from before that are just preparation, and after that is just cleaning. RAM, when registers alone won't cut it. Main memory, which in modern computers is always some type of random access memory, stores the dataset on which the computer operates, and only a small portion of that dataset at a time is moved to the registers for easy access from the ALU. So this memory are program in which only small are being put into this source register. Now why is that? To not overload it. The burden is in memory. Take note, this memory is still faster than the usual big memory we have, which is the SSD. So now this we relax our assumption a little bit. Now we have a memory and the register. So instead of just register as our memory, we're now having an outside memory. So here a computer with the register file. So as you can see, here is the registers. In fact, the ALU and the registers are internal parts of the microprocessors. So these are the They're inside of the microprocessors, but main memory is a completely separate component of the computer system that is connected to the processor via memory bus. So the bus or the links connecting the CPU and memory is called the memory bus. Transferring data between main memory and the registers via the memory bus takes a significant amount of time. Again, transferring data between main memory and the registers via the memory bus takes a significant amount of time. So transferring that is kind of like the preparation we're talking about earlier. Thus, if there were no registers and the ALU had to read the data directly from main memory for each calculation, computers would run very slowly. The file clerk model revisited and expanded. For now, suffice it to say that when the boss wants the clerk to work on a file that's not in the clerk's personal filing cabinet, the secretary must first be ordered via a message from the boss to retrieve the file from the storage room in another floor and place it at the clerk's cabinet so that the clerk can access it when he gets the order to begin working on it. So that's a more finer granularity or a more accurate view of how the modern CPU architecture works. So an example, adding two numbers. To add two numbers stored in main memory, the computer must perform these steps. First, load the two operands from main memory into the source registers. So the memory needs to load that two operands from main memory into the two source registers. So it needs that instruction and data to be loaded into the source registers. Add the contents of the source registers and place the result in the destination register using the ALU. After that, the ALU will now execute that instruction and data with the data inside the ALU and then put that in destination register. To do so, the ALU must perform the steps. Read the contents of register A and B into the ALU's input ports. Add the contents of A and B in the ALU or inside the ALU. Write the result to register C via the ALU's output port. So it used the output port to connect the destination register, while the input port to connect to the source register. And then third, store the contents of so those three are for the step 2. Okay, so the third step, store the contents of the destination register in main memory. So that's another cleaning up, shall we say. So since step 2A, 2B, and 2C all take a trivial amount of time to complete relative to steps 1 and 3, we can ignore them. Hence, our addition looks like this. First, load the two operands from main memory into the two source registers. Add the contents of source registers and place the result in the destination register using the ALU. Store the contents of the destination register in main memory. So that is the three step when we have the main memory. So that's a more accurate. So let's go into finer, more detail. So a closer look at the code stream, the program. The term operation suggests a series of simple arithmetic operations like addition or subtraction. But the code stream consists of more than just arithmetic operations. So the code stream is more than just arithmetic operation. Now we will have to be more detailed about this. Therefore, it would be better to say that the code stream consists of an ordered sequence of instruction. So instead of just operation, now we're talking about instruction, because instruction explain or describe more woolly the operation that the code stream actually um, requests to the ALU. Instructions, generally speaking, are commands that tell the whole computer, not just the ALU, but multiple parts of the machine exactly what actions to perform. So when you say operation, you're just talking to the ALU. But when you're talking about instruction, you're also describing the other parts of the machine, such as how memory loaded to the register, etc. So what are the general instruction types? Instructions are grouped into ordered lists that, when take as a whole, tell the different parts of the computer how to work together to perform a specific task, like grayscaling an image or playing a media file. So these encompass more of the structure of how everything in the computer interconnects or work together. So you don't just need to execute some calculation properly here, you also need to execute some other parts of the system without breaking that system. Kind of like in design, when you're trying to create an app, you don't just achieve some goal, you also need to achieve that goal with respect to other goals. So the system is now interconnected. Now it's the same instruction on the system. Whenever you're trying to describe instruction, you're also talking about the interconnection of the system. That's why in programming, if you're programming, you're essentially doing a lot of instruction. Because if you're talking about instruction, other parts of the system may be affected by your program. That's why it's not easy to create some features on the web application, because it's interconnected. Now, in a modern RISC microprocessors, the act of moving data between memory and the registers is under the explicit control of the code stream. So for RISC microprocessor, the uh, policies, or the control for moving data between memory and register, the slow part or the preparation, are being handled by the code stream or the program. So if a programmer wants to add two numbers that are located in main memory and then store the result back in main memory, he or she must write a list of instruction program to tell the computer exactly what to do. The program must consist of, so like loaded in, you're just not talking about operation, you're talking about the instruction from loading it to the register, getting it out from the destination register back to the memory, and presenting it to the pixel. So we discussed this earlier when we talk about the sequence. It could be a programmer putting instruction. Yeah, that's actually accurate. More accurate way of describing the instruction, or the instruction type. So here, I'll load instruction to move the two numbers from memory into the registers, and add instruction to tell the ALU to add the two numbers. A store instruction to tell the computer to place the result of the addition back into memory, overwriting whatever was previously there. So again, we are overwriting memory because memory is never deleted, it's just overwritten. These operations fall into two main categories. Arithmetic instructions. This instruction tell the ALU to perform an arithmetic calculation. For example, add, sub, mul, diff. Memory access instructions. These instructions tell the parts of the processor that deal with main memory to move data from and to main memory. So it's still on the processor, but they're connecting that part of the processor that communicate or understand the language of memory, that put the data from memory to I think that's memory bus, from memory to register, and from memory to source register and from destination register to main memory. So those are the part of memory access instructions. So note, we'll discuss a third type of instructions, the branch instruction, shortly. Branch instructions are technically a special type of memory access instruction, but they access code storage instead of data storage. So it's part of this memory instruction, and they access the code storage instead of the data. So as you can see, we have a separated part, or space, address space for memory in the operating system for code, heap, and data, right? So here, for the ones talking to the code, we actually have branch instructions, or a special type of memory instruction, and they access. So they are the one responsible for accessing a code. When we say memory access instruction, they define both the instruction for talking to the source and destination register, right? The memory bus. But here it's specifically defining only the code, not the data part. That's why it's part of memory access instruction. The arithmetic instruction fits with our calculator metaphor, and is the type of instruction most familiar to anyone who's worked with computers. So again, the arithmetic instruction fits with our calculator metaphor, and is the type of instruction most familiar to anyone who's worked with computers. Instructions like the arithmetic we discuss are, kind of like basic to understand, but for memory, since it's interconnected, kind of hard to get around. But we will gonna dig into that in further details in the future videos. Instruction like integer and floating point addition, subtraction, multiplication, and division all fall under this general category. Note, in order to simplify the discussion and reduce the number of terms, I'm temporarily including logical operations like and, or, not, nor, and so on under the general heading of arithmetic instructions. So again, in order to simplify the discussion and reduce the number of terms, I'm temporarily including logical operations like and, or, not, and so on under the general heading of arithmetic instruction. The difference between arithmetic and logical operations will be introduced in chapter 2. Actually, this and, or, not, nor instruction, we're gonna relax this a little bit in the next video. We're gonna be more specific or differentiate this instruction from arithmetic or simple arithmetic. The memory access instruction is just as important as the arithmetic instruction, because without access to means memory's data storage regions, the computer would have no way to get data into or out of the register file. So it's kind of like the input-output devices, right? To be able to make this useful is you need to have some input, process, and output. The DLW's basic architecture and arithmetic instruction format. The DLW1 microprocessor consists of an ALU along with a few other units that I'll describe later, attached to 4 registers named A, B, C, and D for convenience. So here we're gonna provide an example of a processor that has an ALU that has 4 registers. The DLW1 is attached to a bank of main memory that laid out as line of 256 memory cells. So it is attached, aside from that 4 register, it has a memory bus attached or line to 256 memory cells numbered 0 to 255. The number that identifies an individual memory cell is called an address. All of the DLW1's arithmetic instructions are in the following instruction format. Instruction, source 1, source 2, destination. So these are the format for instruction of the DLW's microprocessor. You have the instruction, whether arithmetic or memory, and then you have a source 1 and then source 2 and then the destination. There are 4 parts to this instruction format, each of which is called a field. So instruction is a field, source 1 is a field, source 2 is a field, destination is a field. The instruction field specifies the type of operations being performed. For example, an addition, subtraction, multiplication, load, store, etc. The two source field tell the computer which registers hold the 2 numbers being operated on, or the operand. So there's the data from main memory, and the destination. Finally, the destination field tells the computer which register to place the result in. So the source, the 2 source field is kind of like the source register, including the, of course, the work of memory of finding the data inside it to be placed on that source register. Finally, the destination field tell the computer which registers to place the result in. So code, add A, B, and C. Comments, add the contents of register A, B, and place the result in C, overwriting what was previously there. DLW1's memory instruction format. In order to get the processor to move 2 operands from main memory into the source register so they can be added, you need to tell the processor explicitly that you want to move the data into specific memory cell. So the connection from memory to processor needs you need to be able to tell that in your instruction, or to tell that to processor to move the data into specific memory cells to 2 specific registers. Kind of like that's the work that the memory did to put that into the source registers, right? So this filing operation is done via memory access instruction called the load. So all of those steps, or all of those work of finding the data within main memory and putting that to the source register are called the load. As its name suggests, the load instruction loads the appropriate data from main memory into the appropriate register, so that data will be available for subsequent arithmetic instructions. So again, as its name suggests, the load instruction loads the appropriate data from main memory into the appropriate registers. So as its name suggests, load instruction loads the appropriate data from main memory into the appropriate source register, so that the data will be available for subsequent instructions, arithmetic instructions. The store instruction is the reverse of the load instruction, and it takes data from a register and stored it in a location in main memory, overwriting whatever was there previously. So the store taking it the data from the destination register, and then overwriting whatever what's there in the main memory, and it used the memory bus as well. An example of DLW1 program. Now consider program 1.1, which is a piece of DLW1 code. Each of the lines in the program must be executed in sequence to achieve the desired result. Line 1, you have you load the number 12 to A, the data in the memory cell 12 to A. read the contents of memory cell 12 into register A. So that's load. Load number 13 to B. So read the contents of memory cell into register B, and then add A, B, and C, and then overwrite it to put that to C. Add the numbers or do the arithmetic instruction in register A and B and store the result in C. Then store C to memory cell 14. Write the result of the addition from register C into memory cell 14. Program to add two numbers from main memory. So suppose the main memory look like the following before running. Program 1 to 1. For number cell 11, you have 12, cell 12, you have 6, cell 13, you have 2, cell 14, you have 3. After doing our addition and storing the result, the memory would be changed so that the contents of cell 14 would be overwritten by the sum of the cell 12 and 13 shown here. So as you can see, cell 14 now is 8 because we added 6 plus 2.